So this leads us into coordination chemistry. And coordination chemistry really boils down to a Lewis acid center and Lewis bases outside of it. And in this section, our Lewis acids will always be transition metals. Transition metals make great Lewis acids like we've seen in previous sections this quarter. And if you have a Lewis acid with Lewis bases around it, it ends up making a complex ion. And sometimes it's just abbreviated complexes, all right? These complex ions, as we've seen, can be super stable and easy to form. In this world, a Lewis base is oftentimes referred to as a ligand. So in the first example equation right there, we've got an iron plus 3, that's our Lewis acid, and 6 cyanides. And cyanide has lone pairs on both the carbon and the nitrogen if you draw out the Lewis structure. Anyway, that's a great Lewis base. So it's going to make a complex ion where the iron's in the middle and the 6 cyanides are all around it. Notice the charges. Iron started as positive 3, each cyanide is negative 1, and there's 6 of them, so negative 6 plus 3, overall complex ion there has a negative 3 charge. The next example is a nickel ion, nickel plus 2, and it's another great Lewis acid. It's going to be surrounded here by ammonia, NH3. Remember, ammonia has a lone pair on the nitrogen. So 6 ammonias can go around the nickel. The charge positive 2 on the nickel goes to the complex ion because ammonia is neutral. These are the ways then you can start thinking about complex ions. So complex ions in this world, or complexes, are really nothing more than Lewis acids, a transition metal, in the middle of these ligands, which are like Lewis bases. We'll see some weird ligands that we're not used to, but that's really all it comes down to. They'll always have multiple ligands or multiple places that you can connect the transition metal to. Kind of cool. So again, the Lewis acid is the metal. That's going to be where everything gets coordinated to. And the Lewis base, which has the fancy name ligand, that's where the lone pairs are going to connect to the Lewis acid. They're going to donate their electrons. And this creates then these molecules or ions. They're covalently bonded, sharing. It's a coordinate covalent bond usually, but that's cool. These things are actually pretty stable. A coordination compound has one or more complexes. Now, a complex ion is something we've seen already, and it's something with a charge. If you can make that coordination or that complex ion a neutral species, it becomes a coordination compound. So if you look at some of these examples, like let's look at this one right here, CONH36Cl3. Well, that's a cobalt, and we're going to see that a lot of times they'll have 6 pieces around them in an octahedral fashion. So the part in brackets is the complex ion, and we coordinate 3 chlorides around it to make it neutral. So that's an example of a coordination compound. The second one has 2 complex ions. This is a copper with 4 ammonias around it, and this is a platinum with 4 chlorides around it. The first square brackets with the copper, that's the positive cation. The second square brackets with the platinum, that's the negative anion. But they come together in 1-to-1. The whole thing is neutral. It's a coordination compound. And the next one is the same thing as well. The coordination number is something that people talk about in coordination chemistry, and that's literally just the number of donor atoms bonded to that central Lewis acid metal atom, all right? And coordination number is usually no smaller than 2, but it can be 6 and even bigger sometimes depending on the metal. So in the cobalt example with 6 ammonias around it, well, there are 6 ammonias, 6 sites of coordination, so the coordination number would be 6. The PTCl4 thing actually has a negative 2 charge, but that's not important here. That platinum has 4 ligands around it, 4 Lewis base chlorides, so the coordination number is going to be 4. Most common definitely are 6, 4, sometimes 2. You can have different numbers. You can have bigger than 6, especially with lanthanides and actinides. But most of the time for transition metals, 6 and 4 are very common, and sometimes 2. If you have a coordination number of 2, then the pieces that connect to the central atom, like with Lewis structures in Chem 222, usually want to be as far apart from each other as they can. So if you have a coordination number of 2, the geometry is almost inevitably linear. And that's a very similar thing to problems like Lewis structures with carbon dioxide. We saw the 2 oxygens wanted to be as far apart from each other as they can. And that's the same way here with these coordination complexes. AgNH3+ is a complex ion. It's great at removing sometimes silver chloride from glassware. But anyway, that would be an example of a linear geometry. The light blue atom in the center would be the silver, and then the dark blue circles on the outside, each of those represents the nitrogen in ammonia. If you have a coordination number of 4, there's 2 possible geometries, and the most common geometry usually is tetrahedral, just like in Chem 222. ZnNH342+ was a complex ion we talked about in the Le Chatelier's principal lab. That actually has a tetrahedral geometry around it. The 4 ammonias try and get as far apart from each other as they can. So is the FeCl4- thing. However, you do sometimes have square planar geometries. Square planar geometries usually happen when the transition metal has lone pairs of electrons on it. So NiCN4-2 has a square planar geometry. The light blue atom in the middle is nickel. The little red dots in the square around it, each one of those represents a cyanide. And you can imagine that above and below the screen, you would have a lone pair on the nickel. That's what gives it the square planar geometry. I would argue that a coordination number of 6 is most common, and in a coordination number of 6, you will have all the ligands in an octahedral field, and that just means all the ligands will display above, below, left, right, forward, backwards kind of things. These are very, very common. So COCN6-3, that weird FeEN3+ thing, which we'll talk about in a little bit, that's octahedral. Octahedral is very common when it comes to transition metals. The charge on the complex ion is going to be found by just taking the individual charges on the metal and the ligands, and you can find out what it is. On the other hand, the charge of a compound, you have to think about cations and anions separately in order to figure out what's going on. On the left is FeCN6-3. That's a complex ion, okay? So if we were curious what the charge was on the iron, we have to go back and remember that cyanide, Cn is a -1, and there's 6 of them, so the cyanides give a total of -6. But the overall molecule has a -3 charge, so something is giving up a +3 to balance that, and that's going to be the iron. So this is an iron +3 center, because +3 - 6 gives you the charge on the complex ion, that -3. I would refer to this as an anionic complex ion. It has a negative charge, so it's an anion, and it's a complex ion. It has a charge. No problem. On the right-hand side, we have a compound, a coordination compound. But if you look carefully, there's a part in square brackets, and there's chlorides on the outside. The parts in square brackets, that's a complex ion. And so what we'll do is we'll figure out what the charge is on the cobalt first, and then figure out what the rest of it is later. Now, NH3 is ammonia, and ammonia is a neutral ligand, so ammonia has no charge. But the cobalt there is being balanced on the outside by 2 chlorides. And since Chem 221, chloride has always been -1, and there's 2 of them, that must be a cobalt +2 center. So in this neutral compound, the +2 cobalt is being balanced by 2 -1 chlorides. The CONH36 thing, that's a complex ion with an overall +2 charge. However, if you complex it with 2 -1 ions, you end up making a compound. So complex ions have a charge, compounds are neutral. Here's a molecule, CuNH32Cl2, and it says, what's the charge on the copper? no problem. Ammonia, NH3, is neutral, so we don't have to worry about that. But you do see that there's 2 chlorides and 1 copper. So chloride, like everywhere, has a -1 charge, and there's 2 of them. Copper is balancing that out. Notice that there's no charge on that molecule. It's a neutral compound, so this must be a copper +2, all right? And again, having all these ions in your brain really helps out. Ammonia is neutral, chloride's -1, all is well. So these ligands, which are really just Lewis bases when it comes right down to it, they're basically just these things with lone pair electrons on them. And the lone pairs push themselves into the empty orbitals on the Lewis acid, making these kind of connections. Now, in coordination chemistry, they talk about dentate. And dentate apparently is a Latin phrase that basically means tooth. And you can talk about the number of teeth on a ligand. So as an example, a lot of the things we've seen so far have been monodentate, which means they have one tooth or one set of lone pairs to attack a metal atom. But we're going to see here in a little bit that you also have bidentate ligands, which means they have 2 places they can connect to a metal center. We're going to look at tetradentate ligands, where they have 4 places to connect to the metal. And we'll even look at some hexadentate ligands, 6 places to connect to a metal atom. If you don't know how many connections there are, you can call it polydentate. That just means 2 or more donor atoms. And sometimes they refer to these as chelating agents. I can never say that word, sorry. A chelating agent is just a polydentate ligand that can be used to surround a metal and sometimes pull it out of solution and stuff like that. Monodentate ligands are very common, and we've seen quite a few of these already in our chemistry classes. Water is a great monodentate ligand, all right? It's small, relatively. It's got good lone pairs on it, so it connects well to the metals. And I would argue that any metal atom in water has water's complexed around it. In this picture, it's kind of hard to see, but at the very bottom, it says CuH2O6 2+. So in the lower part there, that's a water complex of copper. The copper ions have 6 waters around them in an octahedral kind of situation. They're almost always around if you have them. This is the ion dipole force we talked about in Chem 222 and the intermolecular forces. It's pretty strong about getting the metal ions in water, at least usually. So if you do get the metal ion in water, it's usually because the water's around it. Now there's lots of monodentates, all right? We've already seen examples of cyanide, Cn-, ammonia, NH3. You can have nitrites, NO2, thiocianides, SCN, hydroxides. You can have the different halides. CO is actually a possibility, a carbon monoxide. We'll talk about that in a little bit. Even oxide once in a while is a monodentate ligand. So we've seen lots of examples of these already, but here's some more. Here's a cobalt with 6 monodentate ammonias around it. So you know that that's octahedral. The next one has 6 thiocianides around the iron. So that's also octahedral. And again, notice how the charge changes. Both of those are metals with +3 charges, but ammonia is neutral. So the +3 soars on out. On the other hand, thiocyanide has a -1 charge. There's 6 of them, so they cancel out the +3 and end up with a net -3 charge. A bidentate ligand is just a Lewis base, but with 2 places to connect to the metal center, or 2 teeth, all right? And that's kind of interesting. And some of the common examples of bidentate ligands in coordination chemistry include the oxalate ion, which we've talked about a little bit this class, but not a lot. Oxalate is just a big polyatomic ion. A much more common bidentate ligand is the ethylene diamine ligand. Ethylene diamine, so diamine, 2 amines, and if you remember from organic chemistry, an amine is a nitrogen-containing compound. Ethylene is kind of a common name for ethene or an ethane. It's 2 carbons, all right? So ethylene diamine has a 2-carbon center, and on each carbon you have 1 nitrogen, 1 amine group. That's what it is. Now, for this particular lecture, the nitrogens each have a lone pair. And so each of those lone pairs can be used to attack a metal center or attach itself to a metal center. So that's why they call ethylene ethylene diamine, a bidentate. And then there's also the massive orthophenanthroline, which people abbreviate OPHEN. I'll show you a picture of that in a little bit. That's a pretty big molecule. Notice that ethylene diamine is oftentimes abbreviated EN. All right, we saw an EN earlier and I kind of brushed it off. Now you know what EN means, ethylene diamine. So if you have a complex with a bidentate ligand, and assuming the complex is octahedral, you will see fewer ligands. So like COEN33+, that has 3 bidentate ligands around it, and each of those has 2 teeth. So that would be a total of 6 connection points. That's going to be octahedral. The same thing for the chromium oxalate there in the next line. 3 bidentate oxalates can surround the chromium. And the last one is also octahedral too. It has 4 ammonias and only 1 O-phenanthroline molecule. That's a bidentate. Orthophenanthroline is a really big molecule. Here's the molecules written out more like a Lewis structure. So at the top is oxalate. It's a carbon-carbon backbone, and there's double and single bonds, and those bonds will resonate. The stars represent where the -1 formal charge, if you will, is, and the -1 can resonate with a double bond, stuff like that. Ethylene diamine, the lone pairs are on the nitrogen. That's where it connects. And there's the orthophenanthroline monster. You can see that it has 2 nitrogens there on those kind of aromatic rings. That's where the molecule connects to the metal center. That's a lot bigger of a molecule, so it's harder to put more than 1 around a metal center. This is a type of display called ribbon theory, and it's used a lot in biochemistry. And instead of listing all the different atoms and stuff like that, what they'll usually do in ribbon theory is they'll have like a central atom, and then they'll have the main connector atom. So for ethylene diamine, the EN, that would be nitrogen. And then you can see there's like this kind of ribbon right here, and that's just all the carbons and hydrogens and stuff like that, and pieces honestly that aren't as important. The advantage of ribbon theory is that you can definitely see the geometry around the atom in question. And when these molecules get big, that can be really helpful. On the other hand, when you're learning things, it's hard to remember that, boy, each one of those nitrogens has 2 hydrogens and a connection to carbon, etc., etc. So there's advantages and disadvantages, but you will see it more and more in biochemistry, which is kind of cool. Again, ethylene diamine is a neutral molecule like ammonia, so it doesn't affect the charge. Cobalt +3 can put 3 ethylene diamines around it and still be +3. Here's an example of where someone was able to put 3 orthophenanthrolines around an iron +2 center. Now, orthophenanthroline is also a neutral molecule, all right, so it doesn't affect the charge. But the geometry of this I find very, very fascinating, and other people do too. Sometimes people will call this like a propellerane because it kind of looks like a propeller going around. There's a lot of cool kind of geometry things that's going on. In that picture, the red atom is the iron. The blues, once again, are nitrogens, and everything else is basically like carbon, and hydrogens aren't being shown. But I love the geometry. I find that kind of mesmerizing for some reason. But yes, I need to probably go out and get fresh air. One of my favorite molecules is dimethylglyoxime, and that's abbreviated DMG. If we did the QA3 lab in a face-to-face lab this quarter, when you confirmed the presence of nickel, you added dimethylglyoxime to a nickel solution. And nickel with dimethylglyoxime makes a kind of a cool red color. So nickel dimethylglyoxime 2 is actually something that you may have made. But even if you didn't make it, it's no big deal. This is also a bidentate ligand. And you can see in the picture that this dimethylglyoxime thing has, again, 2 nitrogens with lone pairs. Now in this molecule, you're also seeing some hydrogen bonds. That's what the OH bonds are right there. It's another way to help connect these molecules together to make it a little bit more stable. And again, this is a square planar molecule. If you look at that rotating molecule, it's actually mostly 2-dimensional, a flat molecule. Nickel has some lone pairs sticking up and below the nickel. That's why they're square planar. Kind of cool. Here's a structure for ethylene glycol. Ethylene glycol is a diol. You could also call this 1,2-ethane diol if you remember organic chemistry. Anyway, just describe the dentate character, all right? And I was laughing there because I just looked at my answer E, which is 0 dentate, which doesn't make any sense. But anyway, I crack myself up. When I crack myself up, I think it's a personal goal. But anyway, I'm digressing once again. Sorry. If we wanted to figure out how many teeth this thing could have, what you want to do is look for the number of lone pairs. And you can see that there's an OH on the left and an OH on the right. So I would argue that this is a bidentate structure. If you have a lone pair, you have at least the potential for making a connection to a metal atom. Now, the lone pairs can't be right next to each other. You have to have a couple of atoms between them just to kind of keep the distance apart and stuff like that. But I think ethylene glycol could totally be a bidentate ligand looking at that. EDTA is another example of a ligand that's used a lot, but EDTA is very wild. It's considered a polydentate ligand, which means it can have more than 2 or more, but up to even 6 different teeth connecting it to the metal atom. EDTA is really fascinating. It forms 1-to-1 complexes with most metals on the periodic table except for group 1A. And what that means is that if EDTA sees a metal, it basically attacks it, and one metal per one EDTA molecule is like the resulting complex that forms. It does not do very well though with group 1A, so don't expect it to get the sodium out of your diet or potassium or lithium or something like that. EDTA forms very stable water-soluble complexes, which is kind of nice, so you can get them into your bodies and get them out if you need to as well. EDTA has high formation constants. A formation constant is an equilibrium expression for a complex ion, and if the equilibrium constant is high, that means very product favored. EDTA combined with metals usually have very high KF values, so they're easy to form. EDTA is considered a primary standard, and primary standard means that you can keep it literally in like a little container on the shelf and pull it down after a couple months and use it no problem. A lot of materials will take water and hold on to them, or they'll decompose. A primary standard is considered to be pretty stable and usually very it's not into water either and stuff like that. So you can use it pretty readily, which is nice. If you are a fan of bad movies, and I am almost the king of this, the Blade movie, the original Blade movie with Wesley Snipes, he actually used a EDTA solution to fight vampires. And EDTA, the idea is that EDTA would surround whatever metal the vampires have in their blood and cause them to do some crazy things. If you do happen to see the original Blade movie, please laugh with me. I really do kind of like that movie, I have to admit, but you can laugh at it with me. It's quite all right. Anyway, if you see it, all right, EDTA. EDTA looks like this. This thing is called ethylene diamine tetraacetic acid, and EDTA has up to 6 possible dentate positions, and each of those little stars up there represents one of the places where it could make a connection to a metal. And you can see that each one of those star places has a lone pair of electrons. It's ethylene diamine, so ethylene is the 2 carbons in the middle, diamine, the 2 amine groups, but it's also tetraacetic acid. Now, acetic acid would be CH3COOOH. They're not including either the lone pair or the hydrogen here. Most of the time, for most of these complexes, I would put just another lone pair right there. So this would be the deprotonated version, or the more basic version, if you will, all right? But sometimes the EDTA complexes will actually have the hydrogen there. It just depends. But what's really cool is that this molecule is so big, if it sees a metal, it literally wraps itself around the metal center. And then if it's wrapped around it, you can flush it out with water. So it's a great metal extractor. If you accidentally get metal in there, EDTA will sometimes pull the metal out. Here are just some kind of cheesy pictures showing different combinations of how EDTA works. EDTA, again, does have 6 possible positions. Now, on the left-hand side, it's hard for, I think, anybody to make sense of what's going on. That's pretty ugly. But with ribbon theory, it kind of breaks it down once again. You can see the blue nitrogens, the kind of red oxygens, and the cobalt in the middle. So it's easier, like I said, a lot of times to see the ribbon theory than it is the actual like Lewis structure form. These values are the log of the formation constant. Now, these formation constants are very product favored, which means very large. So if you take the log of the K, these are the numbers you get. And all of these are really big numbers. If you wanted to turn it back into a regular K, you take the anti-base 10 log, you'd go 10 to the power of 25.1, for example, to get what the K is for iron plus 3. So these guys really like to form very high formation constants. And again, that just tells you as a scientist that if you put EDTA in with metals, it's going to pull them out. It's going to surround the metals, pull them out of your own other complexes. Maybe that's a good thing, maybe that's a bad thing, but be careful. And it is kind of a powerful tool sometimes when you're dealing with metals. Now, there are other chelating agents besides the one we've seen, and I just want to briefly go over them. Biochemistry is filled with these chelating agents, which are basically just polydentate ligands. This one is porphine, all right? It's apparently a really popular one in nature. And again, my knowledge of biochemistry is not great here, so I apologize. But with good old-fashioned Google, I'm sure you could find all kinds of cool information. The nitrogens in the middle on the left kind of show where the connections can be made to the iron, and then in the lower right you actually have the iron connected. Myoglobin is an iron-containing protein, and it stores oxygens in cells. And again, if you have like all the atoms, you can't make heads or sense of it. But again, using that kind of ribbon theory thing, then you can actually see what's happening. So in that little part there in the middle, the little blue atom there is the iron. There's a nitrogen kind of 5-membered ring above it, and the oxygen, those 2 little O atoms, is below. And so it's able to hold on to the oxygen until it's needed, then it releases it. Good to go. Oxymyoglobin is another one of these. Again, it's iron. It holds on to the oxygen on one side and that nitrogen 5-membered ring thing on the other side. And again, in biochemistry, you'll look a lot more into this, and I'm sorry I don't know more cool facts about it and stuff, but it's kind of cool. This is kind of a stupid joke, but I had to throw it in here. You know, these stupid memes, I kind of fall for them sometimes, especially when I'm kind of bored or whatever. Anyway, I saw this. It's like hemoglobin, and hemoglobin is connected right now to oxygen, and that's good. But you can see hemoglobin is being distracted by carbon monoxide. I put this in here because carbon monoxide has a higher formation constant to the iron and hemoglobin than oxygen does. So if hemoglobin is around carbon monoxide, it'll take the CO up and kick the oxygen out. And that's bad for our bodies. Our bodies need the oxygen. CO, of course, will kill us. So anyway, stupid meme. I apologize. My poor sense of humor. This is kind of a strange lecture, you can tell.